Traffic classification of mobile apps through multi-classification. Abstract. The widespreading and growing usage of smartphones are deeply changing the kind of traffic that traverses home and enterprise networks and then in the internet. Tools that based their function on the knowledge of the application generating the traffic. Performance enhancement proxies, network monitors, policies, enforcement devices. Imply traffic classification and are thus limited or impaired when dealing with the daily expanding set of mobile apps. Besides the moving target nature of mobile apps traffic, the increasing adoption of encrypted protocols (TLS) make classification even more challenging, defeating established approaches (DPI) statistical classifiers. In this paper, we aim to improve the classification performance of mobile apps classifiers, adopting a multi-classification approach, intelligently combining decisions from state-of-art classifiers proposed for mobile encrypted traffic classification based on a dataset of users' activity collected by a mobile solution provider. Our results demonstrate that classification performance can be improved according to all considered metrics up to 8.1% of F measure score with respect to the best classifier. Further room for improvement is also evidenced by the D combiner performance worker. Index terms, traffic classification, mobile apps, Android apps, iOS apps, encrypted traffic, information fusion, classification combining, multi-classification, introduction, tools like security and the quality of service, enforcement devices and network monitors based their operation on knowledge of applications generating the traffic. The process of associating rivaling network traffic with specific applications of application types is known as traffic classification (TC) and has long established application in several fields, backed by wide scientific literature. First, the global spread and then growing usage of smartphone is profoundly changing the kind of traffic that traverses home and enterprise networks and the internet. As a consequence, both the necessity and the difficulty of traffic classification of mobile traffic have become very high nowadays. Indeed, in addition to traditional drivers for traffic classification of mobile apps traffic has the potential of providing extremely valuable profiling information to advertisers, insurance companies, security agencies, or malicious parties about users. On the other hand, it certainly raises privacy issues, especially in regard to recognition of context-sensitive apps such as health and dating ones. Unfortunately, traffic classification comes with its own challenge and requirements that are even exaggerated in our mobile traffic context. This is usually characterized by the presence of a large number of apps discriminate from and an inadequate number of training samples per app. Moreover, the increasing adoption of encrypted protocols (TLS) makes classification even more challenging, defeating established approaches. Moving from earlier port-based methods to those based on payload inspection, termed Deep Packet Inspection Method (DPI)2, approaches based on the machine learning classifiers are deemed the most appropriate, especially in this context, since they also encrypted traffic (ETA). Analysis 3, 4, 5, 6. Although earlier results have been published on this topic, the traffic of mobile apps is a moving target for classifiers due to its dynamic evolution and mix. Thus mobile total classifications continue constitute an open and evolving research field. In this paper, we aim to improve the classification performance of mobile apps by adopting a multi-classification system (MCS) that is intelligently combined decision from state-of-art classification, specifically devised for mobile and ET classification, and currently considered the best approach in such text 346. To the best of authors' knowledge, this investigation is performed in the mobile context for the first time. The MCS framework has the potential of overcoming the deficiencies of each single classifier, not improve over a certain bound, despite effort in careful tuning and providing improved performance (WRT). Any of the base classifiers also allow for modulating of classifiers section in the for. For this reason, research has focused on MCS is in the last year 7, 8, 9, 10. Based on these considerations, 5 types of combiners proposed in the literature, 11, 12, are here compared, each with different complexity and training set requirement based on a dataset collected by a global mobile solution provider of true users' activity. Our preliminary results show that MCS framework can improve classification performance with respect to the best classifiers considered for the task. Specified MF measures can be improved by more than 8% on the base classifier, thus showing promising results. Our results show that the present approach is a viable path to improve classification of mobile apps traffic, and then there is room for further research on combining algorithms applied to this goal, with evidence of over 23% improvement achievable by ideal combiner. The paper is organized as follows. Section 2. Discuss related literature. Section 3. Describe the considered MCS framework for the mobile. Total classification. Total classification. Experimental results are reported in Section 4. Finally, Section 5 provides conclusion and future directions. State of art of techniques for mobile apps traffic classification. Total classification of mobile apps has been object of huge interest by several recent work, mainly based on ET assumption. Stobar et al. Proposed a scheme for fingerprinting devices by running their traffic pattern through background activities based on 3G transmissions. Bursts of data are considered to evaluate the statistic features. Then, using support vector classifier SVC and k-nearest labels, a model of the traffic to be fingerprinted is built, being capable of identifying similar bursts. The results show that using 15 minutes of traffic testing based on 6 hours of training leads to an accuracy in 90%. Wang et al. Proposed a system for classifying and uses over encrypted 802.11 traffic, reporting results for 13 iOS apps from 8 distinct categories. Data frames are collected from target apps by running them dynamically for 5 minutes and then training a random forest RF classifiers with the proposed set of features. The need for an accurate or ground truth labeling is raised. Highlighted by counterintuitive behavior of some app performance with training time. App Scanner is proposed as a framework for fingerprinting and identification of mobile apps. The fingerprints are collected by running apps automatically on an Android device, and network traces are pre-processed to remove background traffic and eject features. To train an SBC and RF statistical features are collected on a set of packets defined through timing criteria and destination IP address port. See Section 3A. The result evaluated on 110 most popular apps from Google Play Store reported 99% average accuracy in identifying single apps and up to 86.9% in classifying them, outperforming state-of-art alternatives devised for the conceptually similar website fingerprinting issue. 3,4. These latter methods are used also by Alan and Carlo 15 to investigate whether Android apps can be identified from their launch time traffic using only TCP/IP headers. The size of the first 64 packets. They find that apps can be identified with 88% accuracy when training the test sets are collected on the same devices. On the other hand, accuracy dropped significantly up to 26 for the best classifier when the OS vendor different state-of-art approaches 6, 16, and 17 considered in this work outperformed those analyzed in 15 also in terms of other performance metrics. Sections 4. Others aims at identifying fine-grained user actions within mobile app traffic. Continue later. Recognize specific actions that users perform while running a certain app, based showing performance that vary with the devices being tested, but reach 78.04% precision and 76.04% recall on average. Although not focused on mobile apps, though readily adaptable to this text. The work in 16 proposed a machine learning-based multi-level framework to identify services running within HTTPS connections without relying on specific header field prone to alternation. The evaluation based on real traffic showed high identifiability of encrypted web services. Finally, Tonganuka reviews challenges and techniques for the TC total traffic classification and app identification. The presented approaches are mainly based on signature generation and fingerprint extraction from mobile traffic payload and apps metadata, as well as from third-party services. For example, advertisement and profiling traffic. Nevertheless, the problem of dissecting it is there bypassed by considering many in the middle solutions, suitable only in controlled environments such as enterprises. Traffic classification and work. In this section, we introduce terms and concept regarding traffic object, define the features extracted from observed traffic and adapted for classification, describe the classification algorithms considered as base classifier and the fusion techniques adapted for their combination. A. Traffic view, a common total traffic classification. Traffic classification object is the byflow, defined as a sequence of packets sharing the value of the transport protocol, source IP address, source transport port, destination IP address, destination transport port, where source and destination can be swapped. On the other hand, in this paper, network traffic is decomposed into service bursts, leveraging the notion introduced in 13 and 6.18 for mobile phones identification and mobile classification respectively. More specifically, a burst 13 is defined a sequence of packets having interpacket time smaller than given threshold, named burst threshold, here set to 1 second as suggested in irrespective of their source of destination addresses, as well as of the byflow they belong to. Accordingly, a service burst is then a set of packets within a single burst that belongs to byflow sharing the same transport protocol, destination IP address, and destination port number. We remark that this notion has been used previously 6,18 under the name of flow. However, in order to avoid any ambiguity with the common and established definition of flow 1, we will refer to the decomposition used 6,18 as SB. Statistical features. For the purpose of traffic classification, we will consider features which are either related or extracted by statistical mean. From the vector packet lengths for each SB, 3 packets series are considered: incoming packets only, outgoing packets only, and third, bidirectional traffic. The following features can be identified for each of these services: vector of the packet lengths with the sign indicating directions, minimum, maximum, mean, median, absolute deviation, standard deviation, variance, skew, and characteristics, percentiles from 10 to 90 with 10% increment. Additionally, for the incoming and outgoing package series taken as a whole, the joint histogram of packet lengths in both directions can be considered 3,4. Finally, in the following, the set of M features adopted by each classifier will be generically indicated with F1, Fm, or collectively as F, and the set of classes F as C, classification algorithm adapted based classifiers. In this section, we listed state-of-art approaches adopted as based classifiers. We briefly described their main properties and motivation that guided us to their choices. For all of them, we have carefully reproduced the exact implementation and executed them with the same parameters as described in the respective works, to which we refer for further details. LIB and B in Liberator and Levin for two classifiers were proposed, one based on the Jaccard Similarity Index and another based on the well-known naive Bayesian learning techniques. It was observed that the naive Bayesian enjoys attractive performance and increased robust than Jaccard-based classifiers if IP packets are padded. Therefore, we consider MB-based approach as a based classifier, LIB-MB. The MB naive Bayesian assume class condition independence of the features, F being not the cases for real-world problem but working well in practice, and evaluate the probability that an unraveled test instance represented by Ft belongs to each class's Ci, i.e. the post probability through the Bayesian theorem. C alpha denoted proportionally. Each term PCI denoted the period probability that a general sample from the dataset will belong to Ci and is estimated from the training set population, while each PDF is estimated through a Gaussian corner density estimation. The fine-grained feature that employs is the joint histogram of packet lengths in both incoming and outgoing directions. Her pure, her TF, her cos. The study of Herman et al. Proposed the use of multinomial MMB, multinomial MB, Bayesian classifiers adopting the same set of features as LIB-MB4 but differing in the building assumption. Indeed, the MMB classifiers treating the FMS as free sequences of a certain value of categorical random variables and then compares the sample histogram of each test instance with the aggregate histogram of all training instances per class. Then the evaluation of the conditional PMF is different from LIB-MB and equals P, where P, rho m denoted the probability of sampling the m feature. This implementation is referred to as Herpure in our analysis. The MMB classifiers was also employed in 3 with I term frequently, TF, and then inverse document frequently, IDF transformation, both with or without cosine normalization. The variant adopting TF transformation without and with cosine normalization have been also compared in 6 and are referred in our analysis to her TF and her cosine respectively. TRF and then T SVC is Taylor et al. For response 2. Approaches for mobile air traffic classification response identification were proposed, leveraging both an SVC and then RF on SVC is a supervised model that represents the training samples as point in a future vector space. The aim of training phase is find a set of hyperplanes dividing this space which provide the best class separation. Then during the classification phase, the SVC simply classifies U-point according to portion of space they fall into. On the other hand, RF is an ensemble classification method taking advantage of several decision trees built at training time in order to form a stronger classifier. An RF combines the idea of bootstrap aggregating, bagging, and random feature selection to construct a collection of tree with controlled variance, thus avoiding overtraining. In 6, these classifiers were fed with either I row vectors of packet lengths of second statistical features, with the latter approaches leading to the best classifier, RF with statistical features. For this reason, we consider both RF, TRF, and SVC, TSVC based on the set of 40 statistical features extracted and selected as a 6 cart. Several works performed TC by means of decision trees, C4.5, C5.0, and they are constrained. In this paper, we leverage classifier and aggregation tree, CART, a very similar variant of the C4.5 algorithm, constructing binary trees exploiting the features and threshold that ensure the maximum information gain at each node and allowing to perform both classification and regression tasks. For example, with categorical and numerical target values respectively, the classifier fusion techniques, different classifier fusion rules have been proposed in the literature 7,11. In this study, we will focus on these based on type 1 classifiers. For example, those that output only the predicted classes, implying the least requirement for designers. Before proceeding, we record the definition of confusion matrix 11, specifically the ij's entry of the confusion matrix case classifier ek denoted the eijk represent p. For example, probability of the case classifier of deciding for j's class when the i's class is being observed. Clearly, the matrices ek and the priority PC employed by combiners are typically estimated using a set of data, namely a validation set, different from both the training and the test set. In this study, we will consider the following combiners, whose decision will be generically denoted with D0. Majority voting. The guess class is the one voted by relative majority of classifiers. Weighted majority voting, WMV. The vote of each classifier is weighted by its relative confidence. The combiner output is the average max. Denoted the subject of classifier having decided for I. Naive Bayesian. The guess class is the one which maximizes the post-priority probabilities based on conditional independence of classifiers. That is like this. Behavioral knowledge space method. This approach removes the conditional independence assumption of MB combiner via multinational counting on the jointing classifiers space D1, dk. More specifically, the validation set is used to estimate the posteriori probability PCID for each CI and for each value of the space complexity is the 0LK, which requires a large validation set for training. This in turn allows labeling each possible value of D with the most likely classes according to average max and constructing a lookup BKS table. Then during the test phase, each new DT provides an index to retrieve from BKS table the estimated classes D0. Next method, construct the same table as BKS, but to reduce the overfitting, consider the 95% confidence intervals of the frequencies in each unit. 11. If there is overlap among the intervals, there is no dominating class for labeling the testing instance DT. In this case, the least wrong classifier among the K members of the pool is identified based on confusion metrics and authorized to assign the class to that unit. For a complete comparison, we will consider also an Oracle combiner or for example, ideal upper bound on the performance corresponding a combiner correctly classifying a test sample if at least one of the base classifiers provide the correct decisions. The approach introduced in section 3b, the minimum 3SB ranks considered in this paper is 7, suggested in 6. Since the shortest sequence of packet representing a meaningful data transfer, which include the TCP handshake and an HTTP request response with a corresponding X. Then after burstification, we obtained about 29,617 response. 24714 labeled SBs composing our dataset. Additionally, due to severe imbalance in the number of instances for each app, this is especially true for the least observed ones, figure 1, reporting the empirical CDF of the number of SB per app. An oversampling procedure has been applied to the dataset. More specifically, we applied the synthetic minority oversampling techniques SMTE 21 to app with the number of SB less than 13th percentile of the distribution in figure 1 in order to obtain reasonable number of sample per app. SMTE is one of the most popular approaches For database class minority oversampling, we remark also that the result obtained with different percentage SMOTE, for example, corresponding to the 14th and 15th percentiles, have shown no discrepant relative performance among the classifiers combiners considered in the follows, thus underlining the stability of the considered dataset. Finally, after applying SMOTE, we obtained 3,618 responses to 25,465 SB, composing our dataset with the least popular classes composed by 155 response 152 SBs. Classification results. In this section, we show results pertaining to experiment on the dataset described in section 4/A, obtained by application of the proposed MCS. See section 3. Our comparison will be based on the following performance measures: overall accuracy, precision, and recurse. Since the latter two are defined on a per app, per class basis, we will employ their arithmetically average these macros versions. Additionally, we will consider the F measure so as to account for the both effective of precision (PREC) and then recall (REC) in the concise fashions. Furthermore, we will also consider confusion metrics of classifiers, response combiners to provide their complete performance picture and identify the most frequent misclassification patterns. Finally, the considered setup will employ a random training validation test set splitting with corresponding percentage 50, 25, 25%. First, in tab 1, we reported the performance of all the classifiers considered in section 3. In terms of these measures, also for completeness, we report the accuracy and recall achieved by the ORA. First, TRF, HERCOS, and HERTF achieved the highest performance, WRT, the considered measures. Thus, quality agreeing with the result in 6. Nonetheless, apparent from ORA result, apparent from ORA result, the best accuracy response recall of basis classifiers can be virtually improved by means of the proposed MCS up to 90%, response 22.9% for Android and up to 20.1%, response 23.8% for OS. Respectively, these results confirm the appeal of adapted fusion techniques. To this end, in tab 2, we show and compare the performance of the considered 5 combiners. Additionally, to assess the improvement achieved by combining techniques, we have reported in the column BioMBC the maximum improvement over the best classifier for each metric. Overall, the set of combiners is always able to provide an improvement ranging from 2.6% accuracy on iOS traffic to 6.1% F measure on Android traffic by means of the diversity principle, representing the milestone for adoption of classifier fusion techniques. However, different approaches result best according to different performance metrics. Specifically, MB is able to provide a good improvement with respect to the best classifier for accuracy and recall. Differently, MV and WMV results appearing because of the remarkable improvement in terms of precision and F measure over the best base classifier between 5.6% and 6.1%. Interestingly, MV, WMV, and MB collectively provide the highest performance. This is explained as they are less prone to overfitting and have less training requirement, and last but not least, they also enjoy lower complexity, WRT, WR, and BKS. The comparison of confusing metrics of MB figure 2A, figure TRF, figure 2B also reveals homogeneously reduce the occurrence of misclassification patterns. Finally, in Tab 3, we preliminarily investigate the effect of subset selection on the F measure of the 5 combiners to improve performance further, possibly reducing complexity. Having different optimization criteria combiners, we adopted a heuristic approach informed by diversity of classification method and iteratively removing the worst perform classifiers. From inspect of results, it is apparent that subsets considered are helpful in slightly improving the performance of all combiners and equally important to reduce complexity by a judicious selection of the base classifiers except for BKS, which does not generally benefit from subset sections. Interestingly, the best performance is achieved by combiners which employ a reduced set of classifiers. Conclusion and future directions. We tackled the TC of mobile apps by means of MCS employing 5 well-known combining methods in conjunction with 7 state-of-art classifiers specific of suitable for mobile traffic. The evaluation of combining techniques has been performed on an actual dataset describing traffic from 49 responsive 45 Android response iOS devices. Results have shown improvement of the performance by MCS over the basis classifier up to 8.1% in terms of F measures. Also, the ORA and the preliminary subset section performance have under that there is room for further improvement toward optimal low complexity. Combination of the base classifiers. Future direction will include deeper analysis with an enlarged pool, advanced fusion techniques possibly based on type 2 to 3 ranks and measurement level classifiers 11, intelligent pool subsections, the evaluation of sampling impact 22, and the implementation of classifiers and combination techniques TIEA.